Hi everyone, welcome back to the fourth video already in this installment of the series for the analysis of N of 1 trials. In our last video we created our very first Bayesian model to play around with, and we obtained this posterior distribution of the probability of water based off our small model of the Earth, where we sampled and got 6 observations of water and out of the 9 total observations, and generated this posterior by sampling across a grid of possible values. Today we're gonna play around with this posterior a little more, and to get started I will show you all sorts of neat tricks that you can do and all sorts of questions that you can answer by starting to sample from these posterior distributions. But first, to get started, we'll expand our search grid a little more. So previously we had a grid that had 21 values. Now we'll try a little bigger grid. This is a grid of 1,000 values, so I'm just going to print the first couple of ones. And you see it takes much smaller steps to search the possible space where the actual proportion of water on Earth may be. Likewise, we input a non-informative prior, so there's 1,000 times we repeat the value of 1, meaning that each and every of these prior probabilities is equally likely according to us. We have the same data, so 6 times water out of 9 tosses over a bigger grid. Again, we calculate the posterior, standardize it so that it sums to 1, and we plot it. And now we see that our plot, let's zoom in, it's a series of 1,000 points where we've sampled this posterior distribution. And it's a nice smooth curve now. Now we're going to do something that's a little different. So instead of using the entire posterior, like we did when we had only 21 values, we're going to sample from the posterior. And we're going to take, out of this posterior of 1,000 possible values, we're going to sample 10,000 values. And we can only do this if we sample with replacement. Now I'm going to make a plot and put these side to side. So this is the actual sample. So we've got 10,000 samples with the value for each sample, and so you can see that in some of these samples the values are of the probability of water is actually very low, and some of these posterior samples for the posterior value is really high. Through this muck we can't really see what the most likely values are. So again, this is a density plot, and now for the samples that we've taken from the posterior distribution, so the 10,000 samples, and we get a sample from the posterior distribution, which looked very similar to the posterior that we had. And we can, after we've done this sampling, we can do all kinds of things to it and interrogate this posterior to answer some actual questions. So one of the questions that we might have is, okay, so let's count up all the times that the posterior probability of water is less than 50%. In other words, what's the probability of the amount of water on Earth being less than 50%? And here we get our result, and that's 17% or 0.17. We can also construct prediction intervals this way. So basically what we could ask is, okay, what's the number of samples out of this 10,000, which is between 50% water and 75% water. So we simply count up all the times that the sample is between 0.5 and 0.75, and we divide it by the total number of samples, which returns a probability. And this is 61%. So 61%, to be completely accurate, 6,088 of the 10,000 samples were between 0.5 and 0.75, so that's close to 61%. So out of this sampling of the posterior distribution, you can answer all sorts of questions. One of the things that we often get in frequentist statistics is a confidence interval, and this tells us something about what is the likelihood that our parameter estimate, so for instance our mean, is between these and these boundaries. The Bayesian analysis has a counterpart to this, and it's sometimes called the credible interval, so you get the nice CI abbreviation. However, a more accurate term would be the highest posterior density interval, which seems a little bit vague, but what this actually means is that you take the boundaries where most of the probability distribution is at. So for instance, if we take a 95% credible interval, then we would want the boundaries to be where 95% of the samples for the proportion of water would reside. So it would be somewhere between like here and over here, possibly. Obviously, this 95% is just a convention, so we can take other values like 0.89. Why 0.89? Because it's a prime number. And here we see that if we take the highest posterior density interval, which is sort of like the confidence interval, we see that the 89% or 89% confidence interval resides between 41% water and 85% water, approximately. So somewhere between here and here. So that's nice. We can construct a confidence interval which is actually directly interpretable. Like 89% of the values will be between these boundaries, 41 and 85%. We can also have something that's called the maximum a posteriori, which is sort of like our parameter estimate. This is where the highest likelihood of water of the percentage water on Earth would be. To this we use this command chain mode, and it samples from the posterior, and we take the mean of this, and we get the maximum a posteriori estimate, saying that the Earth, according to our model, is 64% water. So to recap, if we've generated a posterior, we can sample from this posterior, and we can even draw more samples than actually is in the posterior distribution, because we're sampling with replacement, and this is not an issue at all. It's just something that's very analogous to, for instance, bootstrapping. That's something that's used in frequentist statistics as well. After we've taken these samples from the posterior, we can ask all sorts of questions, like make prediction intervals, see which percentage of the samples is within a certain range or below a certain value. We can have something like a confidence interval or the highest posterior density interval in Bayesian terms, and we can have a parameter estimate or the maximum a posteriori in Bayesian terms. We will be using this also to answer some questions by the end of this assignment. So try and remember these terms and we'll get back to them. Next time, we're gonna build a Bayesian model for continuous data, which is the next step on our way to get the model for our magnesium data. So thanks for watching and see you next time.